So for this part, we are going to talk about volumes again. So volumes of solid of revolutions, to be more precise. So last time we had two methods in calculating volumes of revolution, or volumes of solids of revolutions. They are the method of disks, and the other one is the method of washers. Okay, the two methods there, it's not they are not really different. In fact, they consider two things. Okay, two different solids. The one is if you don't have any um, hole in the solid, and then the other one if there are some holes. Okay, so if there are no holes, you use the method of disks, and then if there are holes in your solid, then you use the method of washers. So here we will talk about another method. It's called the methods of cylindrical shells. Okay, so for this particular method, this can solve the volumes of solids of revolutions, whether there is hole or not. So this method is applicable to both scenarios in the solids of revolutions. Okay, so how is this method? So again, let us consider the volume problem. So in here, we let f to be a continuous and non-negative function on AB, and we let R to be the region bounded above by the function y equals f of x, below by the x-axis, and on the sides by the lines x equals a and x equals b. So our goal is to find the volume of the solid of revolution S that is generated by revolving the region R about the y-axis. Take note of that. So we have this function y equals f of x, and then we have the x equals a, x equals b here. We have the x-axis, and this is our region here. Okay, the solid will be obtained by revolving the region about the y-axis. Okay, so this is the axis of revolution, and this is the solid that will be obtained. Okay, now from the previous method, okay, notice that if we do this, we will get some holes in here. Okay, so if we are going to use the previous method, method of washer can be used in order to calculate this. Okay, but look at this. If you are going to use the method of washers, and this is your axis of revolution, okay, this is your axis of revolution, it's the y-axis. So this is the axis of revolution, and this is your y-axis. Using the method of washers, you will need horizontal strips. Okay? So you will need horizontal strips. So again, the axis of revolution is the y-axis. But try to observe. This horizontal strip, okay, will run from this point here, say C, and this one is D. This horizontal strip, it will move from up to down or down to up. The motion is horizontal. Okay? So again, we are trying to use the method of washers. Okay? This means that we will need the highest point here. Actually, let's put this as D. The other guy down here, let's put this as C. So we will need this highest point D here. The lowest point, obviously, it's just C, which is equal to 0. Okay? That's just 0. But we will need this highest point D here. so that we can have the limits of integration. But we will have a problem. If we move these horizontal strips, of course, at this point, the right the right function is your function y equals f of x from this point up to this point here, up to this particular point here. Okay? So this particular point. Therefore, you will need this point also. Okay? Say, let us just put this as d sub 1. So you will need that d sub 1. And then when you go lower, look at this. Okay? When you go lower, the right function here, it's now the line x equals a. Of course, all throughout in here, the left function, it's your x equals, sorry, the right function here, it's the line x equals b. And then in here, all throughout, your left function, it's just your x um, equals a. Which means that if you are going to use the method of washers, okay, in this scenario, given this setup here, okay, given this setup here, then you will do a lot of work. You will have to find this point of intersection here. It's only f of b. Anyway, that's easy. Okay, this guy here, this d sub 1, this is just your f of b. Okay, looking at this scenario. Okay, so there's difference if the graph of the function here is not really nice. But the main point here is you will have to do a lot of work if you are going to use your method of washers. Furthermore, since you are integrating with respect to y, you have to change this y equals f of x. You will need a function x equals g of y. This g of y, it's just your inverse of the inverse of your function f. So you will have to rewrite this again. Okay. Anyway, you've seen some examples where we have to rewrite the function from x in terms of y to y in terms of x and vice versa. Okay. So what I'm saying is, you have the region, your axis of revolution is the y-axis. You will need to do method of washers. And yeah, so you will need to do method of washers, but it will need a lot of work. Okay? So in order to avoid that, okay, in order to avoid that, we will discuss what we call the method of cylindrical shells. Okay? So method of cylindrical shells. So what is a cylindrical shell? A cylindrical shell, it's a solid enclosed by two concentric right circular cylinders. Okay? So you have the right circular cylinder in here, the smaller one, and then there is a larger one. So it's the solid in between them. So it's a shell, okay? It's a shell. You can think of this as a tube, okay? Straight tube. It's a cylindrical shell, okay? And the solid, it's the lining or the boundaries in that tube, okay? So maybe you can think of this as quote unquote washer, but it's taller washer. So if you make your washer taller, then you have a cylindrical shell. So it's just a tube. Okay. If you have a cylindrical shell, you can easily get the volume of this solid. So if you look at this, you have the smaller radius. That's your R sub 1. And then there's a bigger radius. That's your R sub 2. So from the center of your shell going to the surface outside, okay, this is the surface outside. So this is your bigger radius. And then from the center of your tube going to the surface in the inside, okay, in the inside, that's your smaller radius, okay? And of course, the height, you have this, okay? Now, to get the volume of the cylindrical shells, okay, it's similar. You just need to get the volume of the bigger cylinder without the hole, and then you get the volume of the smaller cylinder without the hole, but you subtract that volume of the smaller cylinder from the bigger cylinder. Okay, very much the same on the same with the way we computed for the volume of a washer. Okay, but we will do some more for that. We will do some more computations. So in here, like I said, the volume will just be volume of the bigger cylinder minus the volume of the smaller cylinder if your H is multiplied to each of these. So if you are only looking at this is the area of the circle, the bigger circle. And then this guy here, this is the area of the smaller circle. You multiply it to H, you'll get the volume of the shell. Okay? But remember, difference of two squares. A squared minus b squared. This is a plus b times a minus b. Okay? You have here, you can factor out pi. Then you have here r sub 2 squared minus r sub 1 squared. So again, let me just write this. R sub 2, this is the bigger radius. And then R sub 1, this is the smaller radius. Okay? So if we do this, we will have pi times R sub 1 plus R sub 2 times R sub 2 minus R sub 1 times H. Okay? And then what we're going to do is to multiply by 2. And then, of course, divide by 2 so that we won't change the original number here. Okay? The 2 in the divisor, we will put it as a denominator of your R1 plus R2. Okay? And then if you look at this, formula, well, you have this 2 pi. This guy here, okay, it's just the average of the radius. Take note, you want to get average of two numbers. You add the two numbers divided by 2. But that's what we did in here. You added R1 plus R2 and then you divide it by 2. So that's your average radius. And then there's still the H, that's your height. And then this R2 minus R1, this is precisely the thickness. Okay? This part here up to this part here. This is your R2 minus R1. So it's your thickness. Okay? So in here, the volume can be written as 2 pi times R1 plus R2 over 2 times H times R2 minus R1. Okay? So you remember these names here. You have 2 pi, average radius, height, and then the thickness. Okay? So let us go back to this solid. Okay? Let us try to solve this. Now, take note, if you do washers, okay, if you do washers in here, this will have a lot of work. Okay? because you have to divide it into two parts, this part here and then this part here, and you need to identify this number as well as the highest point, etc. So instead of doing washers, or instead of considering horizontal strips, what we're going to do is to use or to consider vertical strips. Okay? So at this point, let me emphasize. For the discs and washers methods, the strips that you will consider are perpendicular to the axis of revolution. Again, for the methods of discs and washers, the strips that you are going to consider are perpendicular to the axis of revolution. For this method, for the method of cylindrical shells, the strips you're going to consider are parallel to the axis of um, revolution. So this is vertical strip, axis of revolution is also vertical. Okay? And remember, the variable of integration, you can think of it to depend on the strip you are considering. Vertical strips or vertical slabs with respect to x. Horizontal strips or horizontal slabs with respect to y. Okay? So again, to avoid this too much work here, let us consider vertical strips. Strips that are parallel to the axis of revolution. Okay? And of course, this vertical strip, you will move it from these two directions, from left to right. Okay? You move it there, you also move it there. But as you can see, at least on this particular illustration, the above function is consistent to be your y equals f of x. The below function, it's consistent to be your x-axis. So you don't have to divide this into two parts. Okay? So, how do we really calculate this? So, you will divide the interval into interval AB into n subintervals. As usual, so we will have to divide this into n subintervals, and and the subdivision that we're going to do, let's just make it equal. So divide the intervals into n subintervals of equal length. So you will have these rectangles in here, vertical rectangles to be more precise. And if you revolve this, okay, you will see this guy here. So upon revolution, okay, you will see this. And if you look at this, there's a blue here, and then there's gray here, gray again in here. So the coloring in here, okay, alternate gray, blue, so that you will see clearly the situation once we do the revolution. You see this cylindrical shell, this first cylindrical shell here, there's another cylindrical shell here, and then another cylindrical shell here, etc. So once you do the revolution in here, once you do the revolution, you will be able to create these cylindrical shells, okay, coming from the vertical strips that you have. Okay? So let us do that. Fixed n, we divide the interval AB into n subintervals of equal length. Okay? So that your delta x, it's simply your delta x sub k, I mean, it's just your delta x, and it's b minus a over n. Okay? Now, For the kth subinterval, okay, we will choose a sample point. But this sample point, we want this guy here. We want x sub k minus 1 plus x sub k over 2. So we want the sample point to be the midpoint of your subinterval. Okay? So you have the kth subinterval, x sub k minus 1, comma, x sub k. The sample point that you will choose, it's the midpoint. Okay? Unlike in washers and in this, the sample points there, you can choose it to be any inside the interval. It's anything. But for this, we will exactly choose the midpoint. Okay? The reason is for the computation later, we will see we will see that we can use this formula in here. The midpoint, it will become this part here, the average radius. Okay? So we choose now our sample point, and then the slab, after the revolution, the slab that we will create is a cylindrical shell. Okay? And the volume of this cylindrical shell, according to our computation, it's equal to 2 pi times x sub k star. Take note of that. X sub k star. It's this guy here, the average. Okay? Times the evaluation, f of x sub k star, that's your height in here. And of course, times the thickness. But the thickness, it's just your delta x. So if you are looking at this, okay, if you are looking at this here, x sub k, this x sub k here, this will be your bigger radius. Bigger radius. This x sub k minus 1, this is your smaller radius. And of course, this x sub k star, this is your average radius, the one that we need. Okay? So far, so good. And then your height, that's your f of k, or f of x sub k star. This becomes your height, the evaluation at the function. And your delta x sub k, this is your thickness. So if we do that, remember, V equals 2 pi times average radius times height times thickness. And that's precisely this. We have the 2 pi, the average radius, okay, the height, and the thickness. And of course, this is just one of the cylindrical shells, okay? But you have a lot of cylindrical shells here. So you have the volume of the shell here. You can get the volume of the shell here, all the shells here, S sub 1, S sub 2, until S sub n. These are your cylindrical shells. You get the volume of each, okay? And then you add them, and you will get the Riemann sum. The volume of your solid S will be approximated by the Riemann sum. And by letting n approach infinity, okay, the volume will just be this limit here. And if your f is integrable, you will have the definite integral. And look at the formula. Integral from a to b, 2 pi x f of x dx. Okay? So 2 pi x f of x dx. But again, try to remember this. Volume, 2 pi, average radius, height, thickness. Okay? 2 pi, average radius, height, thickness. So this is the method of cylindrical shell. And of course, analogously, we have for the variable y. So in here, we have a function f, continuous and non-negative on the CD. And let R be the region bounded on the right by x equals f of y, on the left by the y-axis, above and below by the lines y equals c and y equals d respectively. Then the volume above by y equals d and below by y equals c. Then the volume B of the solid of revolution S that is generated by revolving the region R about here. This should be about the x-axis. Let me correct this. So this guy here, okay? So this guy here should be about the x-axis, okay? Is given by this guy here. B equals the integral from c to d 2 pi y f of y dy. So to visualize this, say you have this Cartesian plane, this is your y, this is your x. You have the function here. The function must be written as x equals f of y. And then this is your c, okay? This is the c, and then this is your d, and the region will be this part here. Okay, this is the region. It's between the function x equals f of y and the y-axis. Okay, and then the axis of revolution, it's the x-axis in here. So we are revolving about this axis. Okay, so in here, you will have the, for the method of cylindrical shells, your approximating rectangles for the region, it will be horizontal. So horizontal, parallel to the axis of revolution. Okay? Questions? So let us consider some examples. And I hope with these examples here, we will be able to understand this method more. Use cylindrical shells to find the volume of the solid generated when the region enclosed by y equals square root of 2, y equals 2, and x equals 0 is revolved about the y-axis. Let's try to sketch this. So this is your x-axis, this is your y-axis. You have square root of y, okay? So you have here square root of y. So you have y equals square root of x. Why did I say square root of y? So y equals square root of x. And then you have y equals 2. Let's say this is your y equals 2 here. So let's have this y equals 2, okay? And of course, x equals 0. X equals 0, it's just your y-axis. So this is the region, okay? So this guy here, it's our region. Okay? We want to revolve this, okay, about the y-axis. So we are revolving this about the y-axis. Okay? Now, of course, for this, you can easily get or you can easily use the method of disks, and the solution, it's easy also. Okay? So for the method of this, your axis of revolution, it's this y axis. Okay? So the approximating rectangles will be horizontal. Correct? So it will be horizontal. But in here, we are going to use cylindrical shells. So the cylindrical shells, the approximating rectangles must be parallel to the axis. So for the method of cylindrical shells, we will be using vertical strips. Okay? So we will use these vertical strips. Since it's vertical, the motion of this strip, it's from left to right. And therefore, we will need the x coordinates. So we need this intersection here. But this is just y equals 2. Okay? This is at the point y where y equals 2. So this guy here, this is equal to 4. Okay? That's just equal to 4 here. So our integral will be from 0 up to 4. Okay? Now look at this. After the revolution, we will see this cylindrical shell. So we will have something like this. Okay? So you have this hole in here. And then, of course, you will have this part here. It's too much. But we will have this. Okay? And this will be your cylindrical shells. That's your cylindrical shell after the revolution. So this cylindrical shell representing this strip here. Okay? So, let us see. We need the height. We need the average radius. Okay? Average radius. We need the thickness. The thickness, this will always be delta x. And in the integral, this will just be your dx. Okay? But let us look at the average radius. So in here, the radius will be from this point here, from the axis of revolution, going to that strip. But this guy here, it's just your x. The distance from this point here, from this point here to this point here, the distance is simply x. So the average radius here, this is just x. But look at the height. The height of the cylindrical shells, this is the height of the cylindrical shell, correct? It's from this line, okay? It's from this line up to the function. It's from the line y equals 2 to the function y equals square root of x. So the height, it will be 2 minus square root of x. Following? Okay. Therefore, volume, it's the integral. So this strip here, again, will move left to right. Okay. On the leftmost, we have the 0. Rightmost, we have x equals 4. So from 0 to 4. And then you have your 2 pi times the average radius. So it's just the radius of your shells. So it's just x. The height, it's 2 minus square root of x. 2 minus square root of x. And then the thickness, it's just your dx. Let us calculate. You have 2 pi integral from 0 to 4 of 2x minus x times square root of x. Let me write that as x raised to 3 halves. Okay? And then you have this dx. So let us calculate this. 2 pi integral of 2x, that's just x squared, minus integral of x raised to 3 halves, that's x raised to 5 halves divided by 5 halves. And then you evaluate this from 0 to 4. Okay? And then after evaluation, we will have 2 pi times. At 4, you have 4 squared minus 4 raised to 5 halves over 5 halves. And then we have minus 0. This guy here, it's just 0. So if we simplify this, we will get 2 pi 4 squared, that's 16, minus 2 over 5 times square root of 4, that's 2. And then 2 raised to 5, that's 32. Okay? So for this, it's 64 over 5. Let us just simplify the number here, except for pi. So you have 2 pi times over 5. So 16 times 5, that's 80. Then minus 2 times 32, that's 64. So 80 minus 64, that's just 16 times 2. So this guy here, it's 32 pi over 5. So this is the volume of the solid generated. Okay? Okay? Now, just for the sake of practicing the other methods, in here we solve this using the cylindrical shells. Suppose we have the same scenario. but we want to solve it using another method, either the washers or the disk. Okay? So suppose we have the same problem. Instead of cylindrical shells, suppose we remove this. Okay? We remove this part. If I remove that part, you can use any other method. You can use this washer or shells. Okay? But we already did the shell. So let's use the other methods available to us. So in here, you have your x and your y axis. So this is your x axis, this is your y. The function, we have y equals square root of x. And then, so y equals square root of x. And then we have y equals 2. Suppose this is your y equals 2. Okay, this is 2. And of course, your x equals 0, it's just your x-axis. Your axis of revolution, it's still the y-axis. And again, the region, by the way, let us just put the region in here. The region, it's this guy here. Now, recalling the methods that we have, we already used cylindrical shells. So in here, we have a vertical axis. Okay. Let's use a strip which is perpendicular to that. So we have a horizontal strip. Okay. Of course, if you revolve this about the y-axis, you will get a disk. Okay? You'll just get a disk. There's no hole. Correct? Now, this disk will move vertically because it's horizontal. It will move vertically, going up or going down. The highest point, it's 2. Okay? This 2 here. The lowest point will be 0. Since this is horizontal strip, variable is with respect to y. Okay? So we have to rewrite this guy here as x equals y squared. Okay? Therefore, volume. This is the integral from 0 to 2. That's the motion of your strip. 0 to 2 of pi. And then the radius of that disk, it's just from this point up to this point. Or from the function going to the center of your disk. But the function, it's just y squared, x equals y squared. So you have pi radius squared. Then this is with respect to y. So if we do this, we will have integral. So we have pi integral from 0 to 2. Then you have y to the 4 dy. This is equal to pi y to the 5 over 5 evaluated from 0 to 2. So we just have 2 to the 5. That's 32 pi over 5. And that's precisely the answer that we got from the previous one. 32 pi to the 5. Over 5, sorry. 32 pi over 5. It should be because we are dealing with the same solid. We just solved it using different methods. Okay? For this particular example, the solution is quick using the method of this. Okay? In here, the shells, it took us so long. We got several um, several analysis in here. The computation, it's longer in a sense, okay, compared to this guy here. But when you see some more regions, okay, when you practice on them, you will realize which one um, has the best, or which method is the best to use. Okay. Let us consider this. Use cylindrical shells to find the volume. So to find the volume of the solid generated when the region between the curve y equals x squared and the x-axis over the interval 0 to 2 is rotated about. So we have three parts in here. We have the y-axis, we have the line x equals -1, and the line x equals 3. So we'll be using shells for this. Let us see. Let us graph here. So this is x and then this is y. We have y equals x squared. So say this is the graph of that. So say this is your y equals x squared. And then we need the interval 0, 2. So this is from 0 here. And then say this is your 2. And then we need the region between the curve and the x-axis. So between the curve and the x-axis over the interval 0, 2. So if this is your 2, so the region, it's this guy here. Okay? Let me copy this first before I proceed. All right. Then paste it to another page. And then another page. Okay? So for letter A, y-axis. So the axis of revolution, it's this guy here. Okay? And then we have to use shells. Therefore, the strips must be parallel to that axis. So we have this vertical strip. Okay? And if we revolve this, we will get this shell in here. So let me just put it here. In here. That will represent the whole of this shell here. Okay. So height. This is your height. It's from the axis to the function. So height, this is equal to the function. So x squared minus just the 0. So I'll not put it here. It's just your function. Okay? The radius, so let me label this as your height. The radius, or the average radius, okay? It's from the center of your strip going to the center of your shell. Okay? Okay? So this is your radius. So again, this is just, since the axis of revolution, it's your y axis. Therefore, this is just x in here. Okay? Of course, the thickness, it's just your delta x, or the dx when turned to when we turn it to definite integral. This this guy here, this strip will move horizontally. So the leftmost, it's at this 0. The rightmost, it's at this 2. So volume, this is the integral from 0 to 2, 2 pi times the radius, which is your x, times the height, which is your x squared, and then the dx. So if we calculate this, this is just 2 pi x cubed. So if we integrate this, we'll just get 2 pi x to the 4 over 4, evaluated from 0 to 2. So this is just, so if you calculate this, you'll just get 8 pi. Okay? So this is for your letter A. Let's look at letter B. This time, the axis of revolution, it's the line x equals -1. So in here, we have here, say, this is your -1. So the axis of revolution is here. Okay? The axis of revolution, it's still vertical. So using shells, we need the strips to be vertical also. So in here, this is your strip. Okay? If we rotate this or revolve this, definitely you will just get the shells here. Okay? Okay? So you have these shells. And then the motion, it's still, look at this, it's still from right to left, or left to right. So the motion of the strips, it's still horizontal. Therefore, the limits of integration will be from 0 to 2, or will be 0 and 2. The height of this shell, it's still from the function going to this guy here, which is just y equals 0. So let us write that height. This is still your f of x, and that's still your x squared. Okay? But look at the radius of your shells. The radius will be from the strip, okay, from this strip going to this axis of revolution. If this were x, if this guy here was x, this x is just from 0 up to x. So you need to add this part here. Okay? So again, the average radius or the average of the kth subinterval, it will be represented by x. So this is the average of the kth subinterval. That will be represented by x. But your x, it's from the origin. It's from 0. So you need to add this part here. Okay? So your radius, or let me just write it average there. This radius, it will be x minus x minus negative 1. And this is precisely x plus 1. Okay? Because, well, again, you added this. This is your x, and this is 1 unit. So you have x plus 1. Therefore, what is now the volume? Volume, integral. Still integral from 0 to 2. Because this is the leftmost point of the region. Okay? 0 up to 2 in here. So you will have 2 pi times the average radius. It's x plus 1 times the height, which is just x squared. And this is your dx. Okay? Questions? Questions? So I'll leave this set up to you. I mean, you finish this, you find the volume of the solid generated here. Okay? Let's do letter C. So in here, we want to find the volume of the solid if the region is revolved about the line x equals 3. Okay? So let us see. Let me just move this guy here because we will need the space here. So this guy, it's your y equals x squared. For x equals 3, the x equals 3, it's somewhere here. Okay? This is your 3. So the axis of revolution is this line. Okay? So this is where you will revolve the region. I mean, that's the axis of your revolution. Okay? It's still vertical. Therefore, if we use shells, we still use vertical strips. Same everything as in before. Okay? Same everything as in before. So after the revolution, we'll get the cylindrical shells. Okay? And then here you have this guy here. And then you have the hole in here for the shells. That's still your shells. Your shells or your strips will still move horizontally. It's still from 0 up to 2. So 0 here up to 2. So 0 up to 2. Height, Nothing is changed. It's still your f of x, or in our case, it's your x squared. So this is your height. The radius, however, it's this. From, from the center of your strip going to this axis of revolution. So it's from this up to this. Okay? Following? But what's that radius? It is from 3 up to this x here. Therefore, the radius will be 3 minus x. So again, the total, of course, this is your 3. From here up to here, this is x, because that's the center here of this strip. So that's your x. So what is this red guy here? This guy here. It's total 3 minus this x here. So the radius is 3 minus x. Therefore, volume is the integral from 0 to 2, 2 pi times 3 minus x times x squared dx. Okay? Questions? So continue. Find the volume by calculating this definite integral. Okay, that will practice your definite integration. Next problem. Use cylindrical shells to find the volume of the solid generated when the region between the graphs of the equations f of x equals 1/2 plus x squared and g of x equals x over the interval 0, 2 is revolved about the x-axis. Okay? I hope you realize now that the examples we are doing on this method, they are the examples that we did in the previous methods. So you can compare the answers. You should get the same answers, the same volumes if you have the same scenario. Okay? So you have here, you have the region between the graph of f of x equals 1/2 plus x squared and g of x over the interval 0, 2. And suppose we revolve it about the x-axis. So here, so x here, y in here. We have the line. So for the f of x, we have the parabola that goes something like this. And then we have the line. This is too much. Let me adjust this. So we have this, and we have the line y equals x. Okay. So this guy here, it's the graph of g of x equals x. This guy here, this is the graph of f of x equals 1/2 plus x squared. We need 0 to 2. So say this is where your 2 is at. And I think I'm gonna adjust that part. Suppose your 2 is in here. So 0 to 2. So the region is somewhere here. So 0 to 2. So the region, it's this part here. Okay. So in the previous lecture, we did this using method of washers. Okay. Now the axis of revolution, it's your x-axis. So this is your axis of revolution. In the method of washers, the strips will be vertical. That's for the method of washers. But for the method of cylindrical shells, the strips will be horizontal. Okay? So we have a horizontal strip. The motion will be vertical. So if we go up, we have this. We still go up, we will have this. Okay? Let's just get one cylindrical shell. So after the revolution, you will have something like this. Okay? So this is your cylindrical shells. But now, you look at this. You will have to divide this into two parts. Because in here, let me put the division. This part here. On the lower part, the left function is actually not just two parts. You have to divide this into three parts. I just realized that. You look at this. Okay? So if you have the strip here, okay, you will get that. So three parts. On this part, the right function, it's this line. The left function, it's this vertical line. On this part, the right function, it's this part here. It's this line. The left function, it's your parabola. And then lastly, on this part, the right function, it's this vertical line. And then the left function, it's this parabola. So we will have to divide this into three parts. Okay?
Sir,
Yes, question?
could you repeat why it's three parts? I didn't get it.
So again, for this, why three parts? It's because if you look at this part here, the right function, it's the line y equals x. The left function, it's this vertical line. On this part here, okay, the right function, it's this g of x equals x. The left function, it's this parabola, f of x. Finally, on this part here, the right function, it's this vertical line, x equals 2. The left function, it's your parabola, f of x. So at each part, you have different left or right functions. That's why you have to divide it into three parts. And therefore, if you do that, you will need to identify this point here and this point here. But anyway, they are easy to identify. Okay? So in this example, cylindrical shell is at a disadvantage. In the previous method that we use, okay, method of washers, we just need to do one there. In here, we have to do 3 parts. But we are forced to do that because we are asked to use cylindrical shells. Let's look at region 1. Let me label that as R sub 1. So, for the R sub 1, this will be the height. It's it's so thin, or it's not really tall, but this is the height here. Okay, so I hope you saw that guy. So this guy here, that's your height. It's from this line. Okay, it's from this line going to this vertical line. The line here, it's y equals g of x. Okay, or it's your line y equals x. Okay, in here, let me change this, the function f of x. You have y equals 1 half plus x squared. But since we are doing horizontal strips here, okay, we are doing horizontal strips, we need x in terms of y. So we have to rewrite this. This guy here becomes x squared equals y plus or y minus 1 half, or x equals plus or minus square root of y minus 1 half. But we only take here, take plus part. We only take the plus part. The plus part because if you look at this graph in here, if you look at the graph in here, it's just on the positive side of x. So you just have your positive side. Okay, so for the function f of x, we will use that later. We need the function y equals x, or the line y equals x. So for the region 1, height. So how do I do this? So region 1. So we need the height. Okay, height. We also need the radius, or the average radius. Okay. So region 1. Okay. The height will be from this line here going to this. So it's just from x minus 0. X minus 0, or simply x. This guy here, it has equation x equals 0. This guy here, it has equation x equals y. Sorry, the height that we will use, it's not x equals 0, but y equals 0. It's not x minus 0, but y minus 0. Because we need the variable y. Okay? The radius, it's from this guy here, from the midpoint of your strip going to the 0. But it's just y. The value here, it's just y. Because it's just from the strip going to the 0. So the radius here, will also just have y. Let me add this part here. What is the interval? The interval, it's just from this point, it's from this point up to this point. This is the highest point. So this point and this point. But that's just one half. The value of y on that highest point of this region, it's just one half. Why one half? Because you know this is just one half here. Well, it's actually the bottom of your parabola. That's what you know, actually. The bottom of the parabola. And the bottom of the parabola occurs when x equals 0. So in your parabola, in here, when x equals 0, y equals 1 half. So the interval will be 0 to 1 half. Okay? That's for your region 1. Now let us do region 2. So for region 2, you have this region here. The height will be from this line, okay, from this point up to this point. It's from the line going to the parabola. So from the line going to the parabola. So you have the line, which is x equals y, but we need the y variable. So that will be y minus, okay, will be y minus, so it will be y minus this guy here. But we take the plus part, okay? So y minus square root of y minus 1 half. Okay? So again, we just take the plus part of this. So this guy here, it has equation x equals square root of y minus 1 half. That's the height. So from this point going to this point. The radius, again, it's just y. It's just y. This is just represented by y. It's from this going to the x-axis. So still, the radius is y. The interval, what's the interval now? If this were 2, if this guy here was 2, this point here will have y coordinate also equal to 2 because y equals x. The x coordinate here, it's 2, but y equals x. So the y coordinate, it's also 2. Therefore, this guy here, this is just 2. Which means what? The interval will be from 1 half up to 2. Last, for the region 3, we have region 3. Region 3 is, it's this guy here. So if we consider this strip, this is the height. The height will be from this point which is your x equals 2, up to this point, which is your parabola, x equals square root of y minus 1 half. So this will be 2 minus square root of y minus 1 half. Reduce, it's still y. Okay? Reduce, it's still y. It's from this guy here up to this. So it's just y. Again, represented there by y. And then the interval will be from the 2 down here, okay? The 2 on this side, up to the highest point in here. To determine that, you know that it intersected the the graph of the parabola. So we just have to calculate the y coordinate when x equals 2. So this guy here, it's just 1 half plus 2 squared. 2 squared, that's 4, plus 1 half. So this is just 9 halves, which means the interval will be from 2 up to 9 over 2. Okay? Therefore, what is the volume? The volume will be the volume here plus the volume here plus the volume here. So let us write the volume. Therefore, volume equals. All of them will have 2 pi. So I'll just factor out that 2 pi at the very outside. For the first region, the limits of integration are 0 and 1 half. The radius is y. The height is also y. But I'll put y minus 0. And then, of course, you have the dy there. Again, the 0 in here is just for emphasis. The 0 in here, it's just for emphasis. This guy here, it's this vertical line there. It's x equals 0. Plus, for the region 2, we have the integral. This time, it's from 1 half up to 2. Radius is still y. The height, it's y minus square root of y minus 1 half. And then you have the dy. Okay? So that's for the region 2. And then you do the region 3 plus integral. Region 3 is from 2 to 9 halves. Radius, it's just y. The height, it's 2 minus square root of y minus 1 half. And then you have the dy here. And then you close the parenthesis. So this will give the volume of the solid. Okay? Try to calculate this. Okay? The volume will be the same as the one we obtained from the previous method. Okay? So we want the volume of the solid generated when this region uh, between the curve y equals x squared over the x-axis over the interval 0, 2 is rotated about the line y equals -1 and y equals 5. So it's the same situation from before, but this time the axis of revolution is different. So let's start with letter A here. So this is your y equals 1, or maybe y equals -1. And then we revolve this about this line. We use cylindrical shells. Axis is horizontal. Strips must also be horizontal. Okay? After revolution, we will have this guys here. We will have this strip here. Okay? The strip is horizontal, motion is vertical. So in here, what's the highest point? If x equals 2, this is equal to 4. Okay? So the motion is vertical, going up, going down. But all throughout, the right function, it's just this line here. The left function, it's just this parabola here. So let's start. What's the height? The height, it's from this up to this. So from this point here up to this point here. So it's just 2 minus, keep in mind, this is horizontal. The equation was y equals x squared. Okay? But we need x in terms of y. So this is x equals plus or minus square root of y. But then again, we are taking the positive side because our x has to be positive. This is the part of the parabola we need. The x's are positive in here. So we just take the positive side. So in here again, take plus side in here. So the height, it's 2 minus square root of y. The radius, the radius, this is your y in here, okay? But you need from this strip up to this axis of revolution. So the radius, this will be y minus -1, or it's just y plus 1. Therefore, volume, this is the integral from 0 to 4. So from 0 to 4, 2 pi times the radius, it's y plus 1, times the height, 2 minus square root of y, and then we have the dy. So I will leave this to you again, but that's the setup. Okay? So again, the radius, it's y plus 1 because again, you have the representation here. This is your y, and the distance here, it's 1. So y plus 1. Okay? Let's do the second part. Let's do letter B. So we pull up that graph again, and let me adjust this y coordinate, or the y-axis rather. So this is your y. So like before, we found that this is 4. So y equals 5, it's somewhere here. So we need this line. This is your y equals 5. And we revolve about this axis here. Okay? And then horizontal axis. So we still use horizontal strips. So this is the horizontal strip. If we do the washers or the shells, well, it's quite big. So maybe you can draw the shells on your own. But anyway, this will be the height. And height, this is still 2 minus. So if we go back to the previous computation, this guy here, it's x equals plus or minus square root of y, and then we take the plus part. So the height, it's 2 minus square root of y. And then the radius, it's from the axis of revolution up to this strip. But again, this strip represented by y. Okay? So if this were y, this is 5 in here. So you have to subtract y from 5. So the radius, this is 5 minus y. Therefore, volume will be integral from 0 to 4. Again, that's still 0 to 4 because the motion is up to that point only. So from 0 up to this point only. So 0 to 4, then 2 pi times the radius, 5 minus y, times the height, 2 minus square root of y, and then we have the dy. So this will be the setup of this um, of the volume of the solid that will be generated. Okay.